Hi guys, welcome to another video on the production of materials, and in this particular video we're going to be looking at galvanic cells. There's quite a lot of detail around galvanic cells, and now that you've had the opportunity to set some up and investigate some of the characteristics of galvanic cells, I think it's time that we just really zeroed in on some of the important terminology that you need to understand in relation to galvanic cells. So to set the context, what happened when we placed a piece of zinc in a solution of copper ions, like copper sulfate? Well, what we found was happening was that the zinc was coming out of the solution, was actually going into the solution, as zinc ions, and the copper was coming out of the solution by taking in those electrons to form copper solid. So what we found was that the blue part of the solution was becoming paler, was decolorizing, and we had copper solid depositing as a precipitate in the solution. When we look at the activity series for the different metals, we notice that zinc is here close to the top, or at least in the top third of the reactive metals, with potassium, lithium right up here, and copper is down here. So zinc is a much more reactive metal than copper. Therefore, it is more likely to lose its electrons than copper, and in fact what it will do is give its electrons to the copper ion, which will shift it back towards the formation of solid copper. So the important thing to remember here is that the more reactive element will oxidize. So therefore, the more reactive element will undergo oxidation. In this case, it's the zinc. The zinc is the more reactive metal, and therefore it's the one that's going to oxidize. The copper is the less reactive metal, and so it is going to come out of the solution and form solid copper precipitate. In this case, we describe zinc as the more powerful reductant because it is causing reduction to happen to the copper. The copper ions is the more powerful oxidant, and in this case it's an oxidant because it's causing oxidation of zinc. Now, it doesn't really matter which way around you look at each of these things. This is really what's going on here. This type of reaction is called a displacement reaction. We can see in this displacement reaction, if we start with a solid piece of zinc, the zinc is going to go into the solution, and the copper is going to come out of the solution and deposit on the electrode. And of course, some of it will actually fall to the bottom of the beaker. You can see that the color between the two solutions has changed. And in fact, if we can get to a point where we may completely decolorize the solution and turn it back to a colorless solution, depending on how much zinc we have and also the concentration of copper ions in the original solution. So what happens if we want to actually take advantage of the fact that the electrons are moving? When we put them in the same beaker, the reaction is a spontaneous reaction, and we find that the zinc breaks down and the copper is deposited. The principle behind a galvanic cell is that we take a reaction which is spontaneous and we separate the components. We separate a spontaneous components. So the zinc is in one beaker and the copper is in another beaker. For this to happen, we need to make sure that the zinc is in a solution of zinc ions and the copper is in a solution of copper ions. Notice that the anion here isn't critical. There are reasons why we might choose certain substances over others, but it's not critical in this case because what is important is the two metallic solids and the corresponding ions. In this case, the anion is just going to be a spectator ion. When we try and when we separate the two reactions like this, we can actually capture the electrons that are leaving one of these half reactions cells and monitoring what happens as it moves to the other one. In the situation that you saw in the previous slide, though, nothing is actually going to happen because we have no pathway for the electrons to move between the zinc and the copper half reactions. We need to ensure that the two reactions are in contact with one another. So if we were to provide a path of conductance, that is, some electrical wires that allow the passage of electrons from one side to the other, can we actually find that the electrons that are produced in the oxidation of zinc will actually travel to the copper? Well, you should already know the answer to this question, and that is we still don't have a complete circuit because we need a complete circuit. And in this case, this is not a complete circuit. Whilst we have a connection from the zinc to the copper, so any electrons being produced as a result of oxidation occurring in the zinc beaker, we can get the electrons across to the copper, but we have no connection coming back the other way. Therefore, this is actually an incomplete circuit. And so therefore, the answer to the question of will this work is no, it won't. So still no reaction because we haven't completed our circuit yet. In this case, what we've done is we've allowed a passage for the electrons to move, but we haven't allowed the passage of the buildup of ions. So when the zinc is oxidized to zinc ions and the copper ions reduce to copper metal, we create a buildup of charge, potentially. Of course, because there's no reaction, this won't happen if they're not connected. This is kind of a theoretical discussion here, but effectively what would happen is we get a buildup of positive charge of lots and lots of zinc ions in the beaker that was on the left, and an excess of the spectator ions, which was the sulfate ions in this case, in the beaker on the right, because the copper ions are disappearing. So how do we balance these charges? We can't have unbalanced charges. So in order to restore that balance, we have to provide a mechanism for the ions to move from one beaker to another. And you know what that solution is? It's a salt bridge. What we have to do is place a salt bridge between the two beakers. This allows electron movement across through the wire and ion movement back through the salt bridge. So if we have cell 1 here, or cell ox here, and cell red here, then the electrons are going to move towards the reduction half cell, and then the anions are going to move in order to try and equalize what's going on. The excess here is where they're in excess, okay, and they're limited here, so they move back, and that allows our passage of negative charges to continue to move through this circuit. So the purpose of our salt bridge is to allow ions to migrate from one cell to another. So here's our salt bridge. Finally, we've got our complete circuit. So the electrons can now move through the wire from the oxidation half cell to the reduction half cell, and the negative ions, the anions here, will move through the salt bridge to try and equalize the charges on both sides. Not only will the positive ions leave the salt bridge and into the reduction beaker, they will leave the oxidation beaker and into the salt bridge. So we've got a couple of things that are happening here. It's kind of like a conga line of charges. The thing that's important is that coming through the salt bridge, if the electrons are going in this direction, then we're going to have negatively charged ions moving this direction through the salt bridge. But equally, we could have positive ions moving the opposite direction. So both of these things can happen. In this case, we've got electrons moving through one part of the circuit and ions moving through the other part of the circuit. Of course, what this means is that you have a battery, or at least a single cell, but that cell is generating a voltage. And it's generating a voltage because electrons are moving from the anode, from where oxidation is occurring, to the cathode, where reduction is occurring. And then the ions are moving, so the excess sulfate ions are going to be moving through the salt bridge, and the excess zinc ions will be moving through the salt bridge as well. Prior to all of that happening, though, whatever salt is used to soak the salt bridge, and this will often be potassium nitrate, those ions will be moving initially to try and counteract the imbalance in cations here and anions here. So we've got a net movement of cations towards the reduction half cell and a net migration of anions towards the oxidation half cell. And you can see the two reactions shown here: oxidation at the anode and reduction at the cathode. So just to give you a little bit of an idea here then, just a few little animations to try and give you a sense of what's kind of going on. The first thing that's going on is electrons are actually moving through from the oxidation half cell into the reduction half cell, and they're going from the anode through the external wire to the cathode. Of course, if we put a device in there which is actually going to take some of the energy out of the cell, like a light globe, then you may actually find that there's sufficient voltage being generated in order for it to light up. In the salt bridge, we should have a cation and an anion, and you'll find mostly this is going to be potassium nitrate. The nitrate ions will move from the reduction half cell to the oxidation half cell, and the potassium will move in the opposite direction. So think about it as a closed circuit where if we have negative charges moving through one way through the external wire, then the negative charges are going to be moving the opposite direction through the salt bridge in order to complete the circuit. And we should know, just with our understanding of positives and negative charges and how they move, that if we have a positive charge, it's going to move in the opposite direction. It's possible, of course, that once all of the potassium ions have moved out of the salt bridge, that they will be replaced by the excess zinc ions that are now building up as a consequence of the breakdown of zinc solid in the oxidation half cell. And likewise, excess sulfate ions may also start to move through the salt bridge once all of the nitrate ions have migrated across. Why do you think it is that most salt bridges are composed of potassium nitrate? Well, the key point here is that potassium is an active metal, and most salts, most potassium salts, are soluble. In fact, it's probably fair to say all potassium salts are soluble. And likewise, nitrate as our anion, all nitrates are soluble. And what we don't want is ions migrating from one beaker into another beaker and then causing precipitation. Because if a precipitate forms, then it's taking one of the ions out of the solution, and hence we may find that we get a change in what we are expecting to happen with our cell. In fact, what will probably happen is the voltage will drop potentially to zero if all of the ions are being precipitated out. So we need to make sure that we have soluble ions that are not going to interfere with our galvanic cell. So just to finish off, and I won't give you a question on this slide, on this particular video, because it's a big one, but there's a couple of things that are probably worth just finally going over. Some technical terms that we need to be aware of. We've talked about the salt bridge. The cathode is the positive electrode. It is where reduction occurs. The anode is the negative, and it's where oxidation occurs. And this is because electrons are being produced here. So they're in excess, and they're going to move through the external circuit to the positive electrode. That's where the electrons are going to go. And they're going to combine with the copper ions in order to form copper solid. The two substances that conduct the electricity in the solution are called electrodes, and the solution, which needs to contain ions because it too will need to be conductive, is called the electrolyte. So the electrode are substances on which the oxidation reduction reactions occur. They can participate or they can be inert. They can simply conduct and allow other reactions to occur around them. They are simply the conductors that allow the passage of electrons through that external circuit. The cathode is the electrode at which reduction occurs. Reduction at the cathode. And the anode is the electrode at which oxidation occurs. We have an ox. And so we need to remember that an ox tells us that oxidation occurs at the anode, and our red cat tells us that at the cathode we have reduction. The electrolyte is the substance which conducts the electricity. So it can be a molten, so a substance which is a liquid, or it could be in solution. And most of the ones that you will encounter are electrolytes that are in solution. This changes a little bit when we look at batteries in more detail, but for our purposes, solutions are fine. One thing which we haven't talked about, but I'll just quickly introduce to you here, is the idea of galvanic cell notation. This is a shorthand way of representing what's going on in a galvanic cell. The oxidation occurs first, so we always have the anode. We have an ox on the left, and we have our red cat on the right. So red on the right, and also if you think anode and cathode, those are in alphabetical order, and in fact so is oxidation and reduction. So no excuses for getting this wrong. You can see here we have our species that is being oxidized and the consequence of that oxidation. Then we have a double line to indicate our salt bridge. Then we have our species which is being reduced and the consequence of that reduction, which is the electrode over here. Very occasionally you may find that if we have, for example, chlorine gas, oxygen gas, hydrogen gas, then that means that the electrode will actually be separated out a little bit, and we usually use a comma in order to indicate that. But ask me for some examples if you need one. Here's an example of what I just talked about, because not all electrodes in galvanic cells are actually participants in the reaction, and here is an example where both reactions that are occurring here do not involve the electrodes. So we've got platinum electrodes which are inert, they do not take part in the reaction, but we have hydrogen gas and oxygen gas. You can see at the anode oxidation occurs, and that is where we have electrons being lost as the hydrogen gas is turning into hydrogen ions. And at the cathode, reduction is occurring, and this is where chlorine gas is accepting those electrons and forming chloride ions. You can see the comma here separates the anode, which is where we start from, platinum for the electrode, then the species that is undergoing oxidation, and then the consequence, our salt bridge here, which just indicates the electrolyte. You can see there's no particular salt bridge in this one because we can have the two solutions together. They're not going to interact, and they'll still produce us a nice little voltage. Then we have the species that is being reduced. So this is oxidized as reduced. And this is the consequence of that reduction. And then we have finally our electrode at the end. Well, that was a lot to get through, so no questions today, but have a look through this and see if you can try and understand what's going on in a galvanic cell. I hope this helps. Thanks for watching.